This class number 19, we are talking about the flexural members. Basically, we are talking about the beam element, and the beam element stability is again the issue. So we'll be talking about the stability of steel beams. Alright, as you might have known a little bit when you took the steel, not advanced, for design of steel structure, the course name might be like that. You saw the design curve for steel beam. That looks like something pretty much like this. So you have quite several limit states for the steel beam design, and the formulation for the steel beam design is involving like so many monster E, C, J, G, W. A bunch of things are coming in like a party of the monster. And well, in the undergrad level, generally you will not have enough time to go through the derivations of the governing modes of the beam element. So you just use the formula given as it's shown in the AISC code, right? But you didn't really came down into the detail of how this formula comes up. So as we are taking this course, it is an advanced steel structure, so we need to dig down into this detail of how the formula was derived. Okay, so first of all, the failure mode of beams, or the, well, let's say the governing governing differential equations for beams, for beam stability are the following. Oops. So first of all, we have for the beam, you will first think of the deflection. The deflection of the beam is going on in the plane of Y and Z. Okay, so just deflection, vertical deflection, I'll say it this way. The second thing, not only that you have the vertical deflection in this plane, but you will also have the lateral deflection. That lateral deflection is in this direction. It is the out of plane direction. What we are doing right now is just the steel plate that is acting like the beam. This is the simple case. First, we will explore into the more complicated cases later on. So first of all, well, this is simplified, and we are not going to talk about warping in this case. So aside from vertical deflection, we have lateral deflection. So this is like a side sway. It is going on in the x direction, and the x direction we define x as the axis, and the displacement corresponding to this x-axis is called the u, displacement. For the deflection in the y, we call the deflection by using the v. So the v is the deflection. U stands for the lateral deformation. Well, let's say the lateral deflection. Okay. The third one, we have the torsional effect. So, three governing differential equations will be listed off, and then we're gonna combine all these three equations, and we're gonna end up with only just one equation that exhibit the behavior that comprise the lateral deflection, the vertical deflections, and the torsional deformation. I should make it clear. Vertical deflection. Basically, this derivation, let me move around something. Oops, down to here. Move up a little bit. Okay, yeah, better space usage. Okay, so vertical deflection, lateral deflection, and torsion. Basically, these three are the governing differential equations for this given case. But when you talk about other cross-section like the I-beam cross-section, so you're gonna have the warping effect. So torsional effect. Not possible for the cross section that we are working, which is just like a plate like this, or the cross section that is like the tube. So no matter what you have, the square tube or the circular tube, these are going to behave in the way that we are going to explore into very soon. Okay, so warping effect is not possible here, but 1, 2, and 3 will be incorporated in this derivation. Okay, now let's take a look at the description of the problem we are looking at. So I zoom down over here. You can see that the dotted line, the dotted green line, stands for the original configuration of the beam. Okay, And the brown line stands for the deform configuration. Basically, if you want to investigate into the stability issue of the structure, you are going to write the equilibrium in the deformed configuration. Thus, when you incorporate the geometry change into your equilibrium, you'll be able to represent or bring up the second order effect that is caused by the deformed configuration. So all the equilibriums will be carried out in the brown line, okay, brown shape geometry. So x, y, and z coordinates are aligned in the following manner. I explained about u and v already. So when our beam deform, I take a cut of the beam, right? I will explain more about the boundary condition of this beam, but initially it is the simply supported beam, okay, subjected to the moment at two ends. Alright, that will be elaborated later. The point is that this is how we call the displacement. So the displacement U stems from the lateral motion, which is a measure to the original configurations, and V, this is the deflection. So from this figure you can get what happened over this given cross section. And also since this cross section will be experiencing the torsional effect, it will rotate, and that's going to cause this rotation, and the angle of rotation is represented by the gamma. Okay, all of these u, v, and gamma are changing along the z direction. Okay, and then we will look at the problem mode by mode, or in 1, 2, 3. That will be one at a time. So first of all, let's consider the deflection in vertical direction. I have okay. So this is the z direction, and if we talk about the vertical deflection, then you're gonna have the y, and v is coming down this direction. Basically, your beam I will use the green line first. Your beam looks like this. So the green line is there. That represents your beam. It is resting on the simple support. Oops. Oh, wow. Okay, come back. Okay, and from this view, what we apply is just only the moment at both ends, such that you have the equilibrium of moment that comes from the moment only. In this case, you are not expecting any shear force in this given beam, right? So this moment is called M0. The reason why the derivation is carried out in this picture in this way, having just the applied moment like this, if you draw the bending moment diagram, you find something pretty much like this. So you have just the constant moment throughout, and you do not have shear. The shear force diagram turns out to be just 0. The reason we do it this way because if you go down into the governing differential equation and you try to solve the differential equation, you're gonna feel the pain if you have some other things in between, like the point forces or the uniformly distributed load, right? That is unbearable, and well, the point is that it is super difficult to cast the equation out of those cases. So the methodologies or the proposed framework and the code of practice just stick with this uniform moment M0 apply on both sides, and then later on introduce you the factors that will help account for the different bending moment diagram. This case here seems to be the worst case scenario. If you imagine when we have just the constant bending moment diagram like this in comparison with other cases where you might have the bending moment diagram like this or like this, or for uniform load like this. Other cases are not as critical as the case where we apply M0 on both sides. So this is the beauty of the techniques that is used for the beam stability analysis. Okay, so we have this view. If we look into the cross section, so you will find that the cross section that takes care of the bending moment, or the cross section that is relevant to the calculation of the vertical deflection, is about this direction. You get what I mean, right? The other orthogonal axis will be relating to the lateral side sway deflection. So it works on a different direction, and I hope that you can pick up the right parameters or right cross-sectional properties for the use of the calculation. So over here, let's take a look. We have this cross-section. I would like to just explain it over here to make sure that you will not put the wrong thing into this calculation. So the moment of inertia about this axis, it is the x-axis, okay? If you can see, I take a look. This is a very good look at the cross section of the beam, and I will see that the x is this line. So you can define this second area moment of inertia by the Ix, and this Ix will control the deflection which is going along the y direction. Okay, right. So I am going to draw the deformed shape of your beam. It's gonna look like this. If we have this deformed shape, then we can draw the bending moment. Oops, too thick line. So this is the bending moment that we have. It is what bending moment is given by the EI, and the I is the I subscript X. Okay. This is multiplied by, well, if you want the moment, you will get the EI multiplied by the curvature. Now, how do we get the curvature, and what curvature is relevant to our calculation of vertical deflection? So look at this. We have the Z and we have the Y. Okay, the curvature will be defined by the second derivative of the displacement along the Y, or it is, let's say, the deformed configuration of the beam, right? The deformed profile is explained by the V, and the V is actually the function of the Z. So we have the second derivative of V with respect to the Z square. Now, we look at this free body diagram. We have only just two things, two components. We have the moment, and this is the applied moment, and this is the internal moment. So we can cast the equilibrium equation out of this information very easily. Okay. So now let me ask you something. This direction of the moment is going along with the magnitude, which is given over here. The magnitude is given, well, the EI is always the positive constant values, but the second derivative of V with respect to Z square, if you want to take the absolute sign out, do we have to do anything with it? So take a look at this. As the orientation of your axis is pointing downwards, and Z is going that way. If you see this case, Z and Y, if it looks like this, this gives you the positive second derivative of V with respect to Z square, right? Because the slope is negative here, and slope come down to 0, and then the slope is increasing as it goes along the Z direction. So this is associated with the positive slope, whereas this one you have positive slope, less positive, 0 slope, and negative slope. This one, the curvature or the second derivative of V with respect to Z is negative. So what do we have for this case? For this case, as it is just the upside down, but actually it matches with this negative slope. So basically you are going to get the sign of the second derivative of V with respect to Z square being the negative values. So if you want to take the second derivative out of the absolute sign, then it is going to be equal to minus EIX d second derivative of v with respect to, okay, and we can write the equilibrium equation. So equilibrium equation, we will set the sigma moment is equal to 0. You take moment at any point you wish. You don't have shear for now. I think I should just make it explicitly to say that the shear is equal to 0. You cannot have the vertical reaction. If you do, then you will not get the equilibrium, because you're gonna have on the other side, oh, theorem answer the negative side. Oh, thank you. Just look at the screen. Okay, so you cannot have reactions if you apply just moment on both sides, of which the magnitudes are identical but the directions are opposite. Sigma moment equals to 0 at this point. Let's call it point P. About point P. So M, well, that depends on the sign convention you want. So if we call the clockwise direction being just positive, then we have the M naught, and then we have the negative sign of the magnitude over here, which is given by minus EI subscript x second derivative with respect to z square, and that is equal to 0. Okay, so you will end up with the line over here, EIX. Well, you just we gotta just rearrange it just a little bit. It doesn't make any major change to the previous line. I ran out of the space. First equation, defined by equation number 1. I bring the whole thing up. Today is Tuesday, and I think you guys have just this class and Dr. Thanakorn's class, the forensic, right? So that's all you have for a whole day. If I want to put another live of this class in the afternoon, that is possible. Okay, I think you had a hard day yesterday already, that you had 2 hours in the morning of finite element, and then 1.5 hour of wind and earthquake, and followed by 1.5 hour of finite element in the afternoon. So that was a very good day for you, and today might be another good day for you if I have energy to do that for you. Okay, so vertical deflection is enlisted already. Now let us look at the next mode. Let me move this thing out. Cut. Okay, drop it far away, just in case if I need to use it later. So basically, let's look at this together. This is actually the elevation view, right? So you just imagine that you are over here and look at it from this way. The support condition is like this, and this is the elevation view I mentioned. So the next view that we are going to look for is the lateral deflection. So your eye is going to be over here and look down this way, so you're going to see the beam undergoing the side swaying condition. Okay, so let me move to the next page, and then we talk about lateral deflection. I think I don't know if the way I just jump back and forth around it's gonna make you feel dizzy or not. Many of you who are the batch of 2018 and 19, so the last 2 years are going to be familiar with my iPad teaching, but I see some of you who are in the former batch watching this video as well, like Laxman or Anas just joined. So you might feel a little dizzy because you used to see me teaching in front of the classroom using the whiteboard, but now the whiteboard, I don't have the freedom to fly things around and to zoom out and in like this. So you might feel a little dizzy. That's the warning. So hi Supun, how are you? You are watching me? Long time no see. Are you going to stop by AT sometime? Okay, so I will just list it out over here. Over here it is the vertical deflection. Okay, and the view is the elevation view, just like this. The next one we have the plan view. And let me borrow the drawings from this one. So, whoop. I just copy, and I gonna move it, I'll paste it here, and I go back and I need to copy something more. Okay, we have it. Now the axis label has to be changed, so as it is the plan view, your eye is over here on the top. You're gonna see the Z axis and the X axis. Okay, so here is going to be your X axis and your U displacement. Okay, as it is the top view, you are going to see the different boundary condition that looks like the following. I draw the, I need a thick drawing, and then I copy this. This case we have the restraining in, first of all, we saw already that we have the pin support and roller support on the other side, that Those are the boundary conditions for the YZ plane. But right now we are talking about the X and Z plane. What you are going to see looks like this. This is a boundary condition that is not so general to your eyes, right? You don't see this generally. So this boundary condition is the rotation prevention. That means your rotation along the Z direction will be restrained like this. Okay. Likewise for the other side. Now, we have all of this regarding the boundary condition that control the equilibrium in the X direction. This restraint prevention does not restrain the moment about this direction. So it is more or less like the roller support like this, or the pin support. Okay, you have the free, your moment has to be 0 at this end. But it can restrain and give you the fixity along the x-axis, so this end will not be moving up or down. That's the condition we pose for this plane. Okay, so we are going to draw the equilibrium. Okay, again. So I take a piece of cut, and from this cut I'll come up with the bending moment, which is in X and Z plane. Oops. The bending moment goes like this. So let's take a look. We are right now dealing with something different than before. So I take this cross section and paste it over here. So the flexures we see in this plane, as your eye is going to be this way here, and what you see is the beam moving along the X direction. So the axis, or the I, second area moment of inertia that control the movement along the X direction, is this one about this axis. So this axis is the Y axis, and then you are going to use IY. So no more IX. I'm gonna use the IY instead. right? I hope you know how we figure out which one is controlled by Ix and which is controlled by Iy, right? As you are structural engineers already, I think this is the matter of fact that you'll be able to see the different bending modes in the two orthogonal directions. Okay, so we are going to use the Iy for this calculation, and then we come back and take a look at this picture. So the magnitude of the moment, internal moment at the cut, can be given by the I subscript y. Now, how do we calculate the curvature? Look at the curvature. Okay, it will be the function of u, right? Because the u is going to describe the deformation within this x and z plane, and u will be differentiate. So we take the second derivative of u with respect to c squared, as you can see here, and then we take the absolute value of the second derivative as shown. The point is that, again, like before, now your x direction is pointing downwards, and this is your deform profile. So the deform profile over here is producing the negative curvature. As it produces the negative curvature, we need the sign to cancel out that negativeness. So if we want to take out the absolute sign, you will have the minus sign in front of the whole thing. Okay. Now, look at this. I told you already that the moment is going to be nice. So moment, is 0 for this case, because the way we apply moment is about this direction. And over here, which is perpendicular to to this. So basically, if we take a look at this axis, move around. Okay. Look at this axis. We have 0. Okay. And likewise for the other end. I think we'll delete this out because it looks quite messy around. Let's just clean it. But I just want to emphasize that how we apply the moment, and it is relevant to just the deflection in y and z plane. Okay. The thing is that now let's take a look at the deform coordinates. So in this picture here, I got to move something a little bit. We have the axis of the normal to the cross section. What would be, yeah, the purple color. So the new axis, which is deformed with the cross section, let me just draw it properly. Oh no. And not so satisfactory for me. The line is not straight. I cannot use the help from iPad because that's gonna put me into the perfect vertical or horizontal line. Jeez, that I do not need that. So I need to use the ruler, and that's why it takes a little time. So ugly. Okay, I cannot do the better one. Okay, so these axes are labeled by for the Z. This one used to be along the Z direction. Now it is, I think this one I can do something with it. Now it is given by Z prime. Yeah, okay, yeah, nice. And the Y turns out to be Y prime. Oops. And X prime. Okay. The X prime looks not right. It was supposed to go this direction, down. Okay. So X prime, Y prime, Z prime, they move just a little bit. And we have the new sets of axes. Then we take a look at this fact. This is the prime axis. X and Y. Yeah. Wait, I change the color first. Okay, this is not prime yet. And then we have the prime axis. Okay. So this is the X prime and Y prime. The angle we have in between, you look at this, you see these definitions of the angle. We call this angle gamma. So the gamma is the angle of twisting of the cross section that we are considering. Okay, so this gamma is going to explain how the X prime and Y prime rotates in comparison with the original angle. So here we describe this by gamma and gamma. And the moment m naught, what color did I use for moment? The red color. So the moment m naught. Now how to explain you so you understand this better. Okay, this is the moment m naught. Now I think you get freaked out. What is going on here? Let's take a look here. I will just need to borrow this picture, so it is 3 by something. Okay, so here is the cross section before the lateral and torsional buckling. So it is the original configuration, but I can hardly rotate the picture in what is this, GoodNotes version 4. I'm not sure if version 5 can do this job well for rotating the shapes, but for version 4 I can only just resize, I can just change color, and that's all, pretty much all. So if your eyes is over here, oh no, so your eye must be here, and then you look, basically you should look, your line of sight is going back like this. So you're gonna see the cross section as shown over here, and as you see the cross section, you see that the moment, right? The moment is given by the double arrow as follows. Okay, so delete it. This ugly eye is going out. And I just need to take a little bit off. Okie dokie. So we're gonna take the moment into the component of x prime, right? Because we are going to cast the equilibrium equation in the deform configuration, and this is the deform axis. You might ask, why don't we have to do anything with it for the elevation view? The thing is that the elevation view, you are dealing with the cosine term, and the cosine term of the small angle alpha, it was not bothered. So you have cosine of angle alpha. When the alpha is very small, then cosine is about 1.0. So you don't need to do anything with it. Oops. The good feature, double tap to change from pencil to eraser is okay. Now we want to make this one into these coordinates, to move it in there. So if gamma is very small, the psi gamma can be approximated by the gamma value itself. So the m y prime, you're gonna have the moment in this y prime and x prime direction, both directions. Okay, the m, when you take the component into the x prime direction, it is about 1.0, so you have the m naught in there. But for the y prime direction, it is gamma times the m naught. And if you take a look at the component in y prime direction, you find that the component of m naught is going into this side, which is opposite to the y prime direction, and then it needs to be accounted for by the minus sign as shown. So we have a couple things. We have the internal moment, and we also have the applied moment, m naught. Okay, so it is time to combine these two together. So we get the EIY summation of moments equals to 0. Just like before. So for here you have the minus sign for EIY, second derivative of u with respect to z square. Okay. And then the moment is given by the minus gamma m naught equal to 0. So we just take out, cancel out the side. We get the equation number 2. Now, we look at the top view still, but we are going to consider the different mode. So it is the torsional mode or torsional deformation. And oops, gosh, okay, boy. Okay, alright. It's all gone. Torsional mode. Torsional deformation. I'll then copy the figure and paste it down there again. Okay, so we'll be focusing on the different thing for here. For this one, as you can put the moment, this is what M naught over there, and you have the deformation, which is given by U, lateral deformation, and we can write down the local coordinates or local axis over here. It looks bad. Okay, yeah, this is better. And the orthogonal direction as well. So this one is the Z prime and the X prime over here. So the moment, which is applied just like this, and we can take the component of moment and find out how much it contributes to the torsion. Okay. Like this. So this angle is given by what? Now take a look. We have the reason why we look at the U, why I wrote out the U. The U explain us the deformed profile that you can see from the top view. So the angle of this deformed profile, I mean the slope, right? The slope is the du dz. So this angle over here is given by du dz. So the component of the moment M0, M naught along the Z prime direction is so the MZ prime is given by the du dz M naught why do we have we not only just have this. You look at this one here, if we write down this, the M naught is actually pointing upward. But now this component in the z direction is pointing to the opposite side, to the m naught. So when you take the component of the m naught into the z prime direction, you're gonna have to put the minus sign in there. Okay, so this minus sign drops in over here. Now, let's come back to the mechanics of material class you learned in your undergrad second year, right? The rotation, I think that time you learned theta equals to TL over JG. Right? Do you remember that? So the T stands for the torque. L stands for your length. Well, this case is applicable when you have the constant torque applied throughout the length, a given length. J, torsional constant. And G is a shear modulus. Which is equal to E over 2 1 plus nu. Okay, and theta is the angle of twist. Okay. For here, the theta here will be replaced by the delta gamma. The change of gamma. So if you measure the gamma from one point to another, that's the rotation. So I'm gonna move around a little bit. So the total change of gamma divided by L is gonna be T over JG, and the torque is then represented by the JG multiplied by the change of gamma with respect to Z. So the change of gamma with respect to Z is the more generalized form of the delta, which is the delta gamma over L. So now we're gonna cast the equilibrium equation again based on the deformed configuration. So we put this up, we set this positive sense of torque being the following. So what we have, we actually have two things. First, the effect from the applied moment that leaks into the Z prime axis. If you cast the equilibrium on the undeformed configuration, you will not have this leakage because the M naught is perfectly perpendicular to the C direction. But now, as we are talking about stability analysis, so we cast everything based on the updated coordinate and the axis. So the leakage from M, which is previously perpendicular to Z, it can come into the Z prime. So we have the JG d gamma dc minus du dc times the M naught equals to 0 as the equation number 3. Or in other words, you can move the du dz around. So I just move this out. Okay. And as a result, I think I can as a result, du dz, we just move things around, jg over m naught d gamma dz, and if you take the second derivative for both sides, second derivative of u respect to c square, it is jg m naught, and then second derivative of gamma and with respect to c square. Okay. Then we will use this given information. We take derivative of du dz because we are going to plug this back into the equation number 2. So this will come into here. So page number 3. Plugging in second derivative of u c square into the equation number 2. So I have the jg over m naught, let me see, times the eiy eiy, and then take this in jg and then d gamma, okay, second derivative of gamma with respect to z, second derivative of gamma with respect to c square, and we have gamma m naught plus gamma m naught equals to 0. So you rearrange all these things into the following form. Now I think you can see the light at the end of the tunnel, because this term here is the derivative of gamma, second derivative of gamma, and here is your gamma. So it is just the ordinary differential equation that you have the solution given in terms of sine and cosine function, plus now m naught square. I take this whole thing to divide all throughout the equation, so we get the m naught square over j g e I y. If you see this thing, I think you start seeing some similarities to the code of practice for the steel design of the beam. You must have seen the EIJG as a part of the formula, and then multiply by gamma equals to 0. And if you took courses like the structural computer method in structural analysis or the structural dynamics, you know how to solve this. Actually, if you have just some basic in differential equation. So we set this up as a k square. So the k will be enlisted over here, equals to just the square root of the whole expression. It take the m outside, so 1 j g e I y. And we have the m naught out there. This is your k value. So the solution to this differential equation, well, this is very good for you because you do not have the term on the right hand side, so you don't have the particular solution. This is only there is only the homogeneous solution to the gamma. The homogeneous solution of gamma is given by gamma. What is the function of gamma? Gamma varies along the x-axis. Okay, so the z-axis. So gamma as a function of the z is given by the a times the sine kz plus the b times the cosine kz. Now gamma, we enforce the boundary condition. The boundary conditions we have at the z and at the L, right? At the z equals to 0 and at z equals to L. So z equals to 0, you have the a times the sine 0, which is 0, plus the b times the cosine 0, which is 1, and the gamma at 0 is equal to 0. The rotation is 0 at 2 points here as shown, the purple arrow. So b is then equals to 0. And as B is equals to 0, the form of your solution is reduced and you end up with A sine KL equals to 0, because at the Z equals to L, then you have no rotation as well. And this makes it possible for two solutions. So the first solution, A is equals to 0. This is the trivial solution. And if the sine KL is equals to 0, well, you find that the K times L has to be the N times the pi, where the N is equals to 0. That's, you're gonna end up with something like trivial solution again. From 1, 2, 3, and so on. But the buckling is going to happen at the lowest number of N. So the KL is equals to pi, or equals to pi square L square, and I take the K from this one here, put it here. So we end up with, actually I don't need to do that. Okay, we end up with the M naught equals to pi over L, and then the square root of EIYJ G. Okay. So we can find out the magnitude of M naught that is corresponding to the lateral torsional buckling of the steel beam. So we account for the lateral instability that occurs simultaneously in the same time with the torsional buckling. We have some further development for tomorrow, that the cross section will undergo the warping effect.